Throw a book into a black hole. The book disappears. It crosses the event horizon, falls toward the singularity, and is crushed out of existence. Everything about that book, every word, every letter, every arrangement of atoms is gone, destroyed, lost. Or is it? This question sparked the most bitter scientific debate of the last 50 years, a debate between Stephen Hawking and me. A debate that started in the 1970s, continued for 3 decades, and ended with Hawking conceding he was wrong in front of an audience of physicists in Dublin in 2004. The stakes were nothing less than the foundations of physics itself. Can information be destroyed? Can the universe permanently lose a piece of its history, or is information somehow conserved, even when it falls into a black hole, even when it seems to vanish completely? I'm Leonard Susskind, and I'm going to tell you why information cannot be destroyed, not as a philosophical principle, as a law of physics, as fundamental as the conservation of energy, violated, as far as we know, nowhere in the universe. Let me show you why, and why it took 30 years and a revolution in how we think about space-time to resolve the question. Start with what seems obvious. Information can be destroyed. Burn a book, the information in it is gone. The words, the meaning, the arrangement of letters, all destroyed by fire. But that's wrong. The information isn't destroyed. It's scrambled, transformed, made inaccessible, but not destroyed. When you burn a book, the chemical bonds break, the molecules combust, heat and light radiate away, smoke rises, ash falls. But every atom that was in the book is still somewhere. Every photon carries information about the chemical reactions that produced it. The ash contains information about what burned. The smoke particles encode the molecules they came from. The information has spread out. It's been dispersed into the environment in a form so scrambled that no practical measurement could ever reconstruct the original book, but it's there. In principle, if you measured the position and momentum of every atom of ash, every molecule of smoke, every photon of light, you could reconstruct what happened. You could work backward and figure out what the book said. This is a consequence of the laws of physics being time reversible. Almost every fundamental law, the equations governing how particles move, how forces act, how fields evolve, works the same way forward and backward in time. If you film a collision between 2 atoms and play the film backward, you can't tell it's reversed. The backward process is just as valid physically as the forward one. And if the laws are time reversible, then information is conserved. Because if you can run the process backward, then all the information about the initial state must still be encoded in the final state. Nothing can be truly lost. This principle is called unitarity. It's one of the foundational assumptions of quantum mechanics. The quantum state of a system evolves according to unitary transformations, mathematical operations that preserve information. You can scramble it, you can spread it out, you can make it practically inaccessible, but you cannot destroy it. Now here's where black holes come in. In 1974, Stephen Hawking discovered that black holes are not completely black. They emit radiation. Thermal radiation with a characteristic temperature inversely proportional to the black hole's mass. A solar mass black hole radiates at about 10⁻⁷ Kelvin, incredibly cold. A small black hole radiates much hotter, and as the black hole radiates, it loses mass. It evaporates. This was revolutionary. It meant black holes have thermodynamic properties, they have temperature, they have entropy, they radiate like hot objects. And given enough time, they evaporate completely, leaving nothing behind but the radiation they emitted. Now throw a book into a black hole. The book crosses the horizon. The black hole gains a tiny amount of mass. Then Over an enormously long time, far longer than the current age of the universe for a solar mass black hole, the black hole evaporates via Hawking radiation. Eventually it's gone. Completely gone. And all that's left is thermal radiation. Here's the problem. Thermal radiation is random. It has no structure. It encodes essentially no information beyond the black hole's mass, charge, and angular momentum. Everything else is lost. The information about what fell and the specific arrangement of atoms in the book, the words on the pages, the history of how it got there is not in the radiation. It's gone. This violates unitarity. Information has been destroyed. And if information can be destroyed in black holes, then quantum mechanics, the most successful theory in physics, is wrong. Not approximately wrong. Fundamentally wrong at a deep level. Hawking accepted this conclusion. He argued that black holes represented a breakdown of quantum mechanics. That unitarity was violated. That information could be destroyed in gravitational collapse. He called this the information paradox. I disagreed. So did Hooft and several others. We argued that information must be conserved, that the Hawking radiation must somehow encode everything that fell in, even if we couldn't see how. That there had to be a mechanism, some process we didn't yet understand that preserved unitarity. The debate became heated. It lasted for decades. And it couldn't be settled by direct observation. We can't actually watch a black hole evaporate, so it had to be settled by theoretical argument. The breakthrough came from an unexpected direction. The holographic principle. In the 1990s, Tooft and I, working independently, realized something extraordinary about black holes and information. The amount of information that can be stored in a region of space is not proportional to the volume of that region. It's proportional to the surface area of the boundary. This sounds absurd. If you have a box, you'd expect the amount of stuff you can put in it to depend on how big the box is on its volume. But for black holes, the maximum information content depends on the area of the event horizon, not the volume inside. Why? Because of black hole entropy. Jacob Bekenstein had shown in the 1970s that a black hole has entropy proportional to the area of its horizon. Entropy measures disorder, but in information theory, it also measures information content. So the entropy-area relationship meant that all the information about what fell into a black hole must somehow be encoded on its surface. Let me be precise about this, because it's one of the most beautiful formulas in physics. The entropy of a black hole is S equals Ka divided by 4 squared, where A is the area of the event horizon, K is Boltzmann's constant, and A is the Planck length, the smallest meaningful length scale in physics, about 10 negative 35 meters. What this formula says is extraordinary. Take a black hole with the mass of the sun. Its horizon has an area of about 14 square meters. Divide by the Planck length squared, and you get roughly 1077 bits of information. That's the maximum information the black hole can contain, not 1077 atoms bits. Individual yes or no questions, the fundamental units of information. For comparison, every atom in the sun, every electron, every quark, described at the quantum level, contains perhaps 1057 bits of information. The black hole formed from the sun's collapse contains 1077 bits, 20 orders of magnitude more. Where did that extra information come from? It came from the gravitational collapse itself, from the exact way matter fell in, from the positions and velocities of every particle as it crossed the horizon, from the quantum state of space-time as it formed. All of that gets encoded on the horizon, not in the interior, on the two-dimensional surface. This was so radical that physicists resisted it for years. How could three-dimensional space with volume, with depth, with interior structure be encoded on a two-dimensional surface. It seemed impossible. This led to a radical proposal. The three-dimensional interior of the black hole, everything inside the horizon is not fundamental. It's a hologram, a projection. The real information lives on the two-dimensional surface. The interior is emergent, reconstructed from information stored on the boundary. If this is true for black holes, then maybe it's true everywhere. Maybe all of three-dimensional space is a hologram. Maybe the universe we experience, with its volume and depth, is actually a projection of information living on a distant two-dimensional surface. This is the holographic principle, and it has profound implications for how information behaves. If space itself is holographic, then the information about what falls into a black hole never actually goes inside. It gets encoded on the horizon. And when the black hole evaporates, the Hawking radiation, over time, carries that information back out. Not in an obvious form, it's scrambled beyond recognition, encoded in subtle correlations between photons emitted billions of years apart. But it's there. Unitarity is preserved. In 1997, Juan Maldacena discovered something that made this concrete: the ADS-CFT correspondence. He showed that certain quantum field theories, theories living in a spacetime with one less dimension, are exactly equivalent to theories of gravity in a higher dimensional spacetime. The field theory and the gravity theory are two descriptions of the same physics. One lives on the boundary, one lives in the bulk. They're dual, they're holograms of each other. This wasn't a vague analogy, it was a precise mathematical equivalence. And it proved that holography could work, that the information content of a gravitational theory could be fully captured by a theory on a lower dimensional boundary. This gave us the tool we needed to resolve the information paradox. If the black hole interior is holographic, if it's dual to a quantum system living on the boundary, then information is conserved by construction. The boundary theory is unitary. It evolves according to quantum mechanics without any information loss. So the bulk theory, the black hole evaporating in the interior, must also be unitary, even if we can't see how from the inside. Hawking conceded in 2004. He accepted that information is not destroyed. He paid off a bet he'd made years earlier, giving John Preskill an encyclopedia from which information can be recovered at will, he said, acknowledging the point. It was a gracious concession, and it marked the end of a debate that had shaped a generation of theoretical physics. But here's what bothers me. We know information is conserved. We have strong theoretical reasons to believe it, but we don't fully understand how. If you watch a black hole evaporate from the outside, the Hawking radiation appears thermal for most of the evaporation process. Only at the very end, when the black hole is almost gone, does the radiation need to encode all the information that fell in. But how does information that crossed the horizon billions of years ago get out in the final burst of radiation? What mechanism transfers it? How is it encoded? This is called the information transfer problem, and it's still not completely solved. In 2012, it got even worse with the discovery of the firewall paradox. 4 physicists, Almheri, Marolf, Polchinski, and Sully, known collectively as AMPS, showed that if information comes out in the Hawking radiation, then the event horizon of an old black hole should be a violent, high-energy firewall that destroys anything trying to cross it, not the smooth, empty space general relativity predicts, a wall of fire. Here's why. For information to escape, the radiation emitted early in the black hole's evaporation must be quantum entangled with the radiation emitted later. But the radiation is also entangled with the interior of the black hole. That's a consequence of how Hawking radiation forms. Quantum mechanics says a system can't be maximally entangled with 2 different things at once. Something has to give. Either the early radiation isn't entangled with the late radiation and information is lost, or the radiation isn't entangled with the interior and the horizon becomes a firewall, or the quantum mechanics we thought we understood is wrong in subtle ways we haven't detected. This is still being debated. Proposals include the interior of an old black hole is connected to the exterior by quantum wormholes. Space-time itself breaks down near the horizon in ways we don't yet understand. The information comes out earlier than we thought, encoded in subtle correlations we're only beginning to measure. But we don't have a definitive answer. What we do know is this: information cannot be destroyed. Not by fire, not by black holes, not by anything. It's a law. But why? Why is information conservation so fundamental? The answer connects to the structure of quantum mechanics itself. In quantum theory, the state of a system is described by a wave function. The wave function evolves according to the Schrödinger equation, which is unitary. Unitary evolution preserves the total information content. You can transform the state, rotate it, spread it out, but the underlying information remains. If information could be destroyed, quantum mechanics would break down, probabilities would no longer add up to 1, the theory would become inconsistent, predictions would fail, and quantum mechanics is the most precisely tested theory in physics. We've confirmed it to extraordinary precision in countless experiments. If it were fundamentally wrong in the way information destruction would require, we'd have seen the failure by now. So information conservation is not just a principle, it's a consequence of quantum mechanics working the way it does. And quantum mechanics works. Every atom, every particle, every quantum system we've ever tested obeys unitary evolution. Information is never lost. Here's another way to think about it. Information is physical. It's not some abstract concept floating outside the universe. It's encoded in the states of physical systems, in the positions and momenta of particles, in the quantum phases of wave functions, in the correlations between distant objects. And physics is about relationships, about how things change, about how the state of a system now determines the state later. If information could be destroyed, those relationships would break. The future would not be determined by the past. Cause and effect would fail. Physics would collapse. Information conservation is what makes physics predictive. It's what makes the universe comprehensible. It's what allows us to run experiments today and predict outcomes tomorrow. Without it, there would be no science. Let me make this personal. When I was arguing with Hawking about this in the 1990s, the stakes felt enormous, not because of ego, though there was some of that, but because the question mattered. If information could be destroyed, then the universe was fundamentally random in a way that had nothing to do with quantum mechanics. Events could happen with no connection to what came before. The past wouldn't determine the future. Everything we'd learned about physics would be provisional, subject to arbitrary breakdown whenever gravity got strong enough. That wasn't the universe I could accept, and I don't think it's the universe we live in. Hawking's willingness to concede showed real intellectual honesty. He followed the evidence, he accepted the arguments, and the community moved forward. But the deeper lesson is this: information is not fragile, it's not easily lost. It's woven into the structure of space-time, into the quantum state of the universe, into every correlation and every relationship between systems. You can scramble it, you can hide it, you can make it practically impossible to access, but you cannot destroy it. Throw a book into a black hole, the book crosses the horizon, it falls toward the singularity, but the information in that book, every word, every letter, every arrangement of atoms remains. Encoded on the horizon as the book falls in, encoded in subtle correlations in the Hawking radiation as the black hole evaporates. Encoded, ultimately, in the final quantum state of the radiation after the black hole is gone. You can't read it. You'd need measurements so precise, so comprehensive, that they're beyond anything technology could achieve. But it's there. The universe keeps a record, perfect and permanent, of everything that has ever happened. That's what information conservation means. The universe has a memory, an indelible, unbreakable memory encoded in the quantum state of every particle, every field, every degree of freedom. Nothing is forgotten, nothing is lost, the past is permanent. And I find that strangely comforting.